So today I'm sort of going to be talking through two models. This is a talk about LLM optimization, but even a very simple LLM is quite complicated. So to start off, we're just going to take, it's an arbitrary model. I just went out and grabbed GNN. And so we're going to work through optimizing that. I just took an example from PyTorch Geometric to familiarize ourselves with the profiling tools. And then in the second half of the talk, I'm going to crack open the recently released Lit Llama and show kind of where we start and then kind of how we can use these tools to optimize this more complicated case. And part of that, we will be looking at more complicated distribution, namely fully sharded data parallel distribution. All right, and of course I have my speaker notes. So yeah, I just went out to, let me arrange all of this so that it is reasonably legible. Okay. A lot of this is just, generic. I didn't do anything. This is just part of the pre-processing. So it comes with the data loader. This is working on the Smiles molecular data set. Then again, we just kind of grab a canned model, wrap up your typical PyTorch training steps. So you grab your data, you zero grad, you call your model loss backward, and then optimize your step. Run it for a while. So the first thing that we're going to add is we're going to invoke the PyTorch profiler. So this is just with torch.profiler.profile, context manager, and then we're just going to run our model for a bit and then emit the trace. So if I go to my run notes, and at this point, this is just our baseline. So I haven't actually done any optimization. And what we'll see once it gets running is it's going to take about 20 milliseconds per run. But this doesn't necessarily tell us how to optimize it. So if I pass this dash profile flag, basically there's just arc parsing in here that's actually going to invoke this PyTorch profiler. Then if we give it a minute to run, and I have backup traces for all of these. So if they take too long to run, I'll just switch to the backups. So the way that we're going to view this, you can view it a couple different ways. TensorBoard will support this. I tend to just drop it directly into Chrome tracing or Perfetto, which is the renderer behind TensorBoard. So if I go and I grab my trace and let's download this, and let's take a look. And this is typically the sort of situation you're in, right? You don't want to start off, hyper optimizing your model just as you develop it, because 95% of it you're just going to throw away because it doesn't work, or you tweak it, or you do some other topology. So you're generally going to get reasonably far into your model development before it actually makes sense to really start optimizing it, particularly if you're in like a researchy kind of context. So if we take this, and by the way, this is all interactive. Yell at me if you have questions or if you can't see anything like that. So we look at this trace. The way that you read this is going left to right is time, and then it's showing you these icicles of the stack. And so we read this, we start, we see a data loader, and then the torch op, this is, so A10 cat, A10 is PyTorch's math library. So this is concatenation, and then internally it delegates to a bunch of subkernels that run things. So if we look at this, it's very hard initially to kind of make heads or tails of this. We see a bunch of disparate ops. There's one annotation here for the data loader, but if we go and we actually look at this, we say, okay, there's a new zeros. It's not obvious that this is like what this is doing, so or why it's here if it should be there. So the first thing that we are generally going to want to do is we are going to want to enable Python tracing. Stop for a moment. So in order to do that, we're going to go over here and we're going to pass with stack. And this is, again, just going to forward the with stack argument to the PyTorch profiler. The way that this works under the hood is that it hooks into the CPython profile API. And so as the torch ops are running and registering the kernels that they're dispatching, it's also inspecting the Python stack frames. And then at the end, it accumulates them all together. And so if we look at this new trace, so then we wind up with something that looks like this. And this is a lot more comprehensible, right? We can see this is the Python function that I wrote. This is right? I can see my model topology. This is, it's the graph convolution, and then eventually it's going to get past the Python and it's going to actually start dispatching torch ops. We also, one of the things you might have noticed that is a little bit curious is if we look at this original trace, we have some kernels, we're doing some work, and then we have this giant stop, and then on a different thread, it picks up work and then continues. Well, the reason for this is that the Python autograd engine actually runs in a different thread. So when you call dot backward, it stops your Python code, sends it off to a different thread in C++, and so you see this giant void in the Python thread where it's calling into autograd, and then down here you see the actual PyTorch kernels, the backward kernels, and there's no Python here because the autograd isn't determined by the Python you wrote directly, it's determined by the autograd graph. So if we look at this, something that you'll notice is it's useful to just initially segment some of these out. And I apologize, it's sort of hard to read this with the resolution, but I'll do my best. We have this big, roughly 15 milliseconds of data loader, just grabbing the next batch. And then we have our forward method, which is about 5 milliseconds. And then we have a little bit longer backward. Now, there's no reason for this get next batch to be on the hot path. This is completely, it could be computed ahead of time, but for the sort of expedience, you say, get next and then model off forward. It happens to be on the main path. Now, data loaders offer a way to distribute this. So if I go to V1 of this code, essentially what you can see here is all I've done is I've gone and taken the data loader, which is a relatively small in-memory data loader, and I've just passed num workers to it. And so this will, under the hood, send it to multiprocessing inside of, you can see my muscle memory is going to slack far too often. I'm going to go straight to the num workers equals 2. And what we're going to see here is that this actually isn't going to do very much for us. Just taking this and saying, okay, I'm going to shove it into multiprocessing and then forget about it. And if we look, it's also worth, I think, looking at the individual steps, right? So you can see as some of them are faster, right? It was about 20, 22 before. Some of them are down to 15, some of them are 50, some of them, right? And some of these are like the boundaries as it starts up, a new run for the new epoch. But even throwing aside these outliers, it's still not a particularly compelling picture for how is this supposed to make it faster. And I bring this up because I feel like this is something that is very commonly the first thing that people go for is they say, okay, my data loader is slow, just throw more processes at it. Just throw num workers and that'll be better. And it also, one of the nice things about these traces is that it will tell us where this is going wrong. So you can see that some of these steps are reasonably happy, right? You can see this one, it's spending a little bit of time in the data loader, but it's mostly in the model. Whereas in this step, right, you have these enormous stalls, right? Your data loader is taking 10 times more than the model itself. And this is another case where the Python is a pretty important part of debugging this story. So you can see that it's doing polls. If we look down at the data, we can see that it's doing a bunch of these copies, reads, receives, copies. So basically the issue is that even when your data loader, you just throw multiprocessing at it, it still has to get all of this data back to the main process. And if that's slow, it doesn't matter if the other process was able to produce the batches really quickly if you can't get them out of the main process very efficiently. And generally with 0 copies and with no locking contention around getting back in. So for the next example, I've gone and I've done a more involved kind of multiprocessing, actually put it in separate processes manually, actually do all the pipelining. There's a bunch of work that you have to do to actually do this. You have to tell it to put it in shared memory so you can get it over. You have to limit the amount of compute that any individual worker can do, because otherwise they'll all try and take over the entire CPU and contend with each other. I don't think it's particularly useful to go through this entire, all of the implementation. Instead, the point that I want to make is just that you have to kind of go the one step further and actually make sure that you are getting the complete naive parallelism and that you're completely decoupling them. And then once you do, right, now you can see we're down to 8 to 12 milliseconds. And if we look at these traces, oh, sorry, I haven't run the Python trace. When we open it up, basically what we're going to see is that the data part is pretty minimal. You basically just go from one step to the next. So if we get this, pull in our now V2. Right, there are still some of these big stalls, although this one's coming from the AutoCAD engine. But if we zoom in on the actual, like this is a model step, and this now looks much better, right? You now have a forward step, you have a backward step, you have an optimizer apply, it's out of the way. And your data is way over here in the corner. Really all this is just copying it from CPU to GPU because it's not worth the complexity to do that in the side process. Now, this is just getting your data off the hot path. Once you've gotten your data off the hot path, that's naively parallel. The model is not. The model has to be run in a particular order. You have to do your forward pass before you can do your backward pass. And this serialization is where a lot of this comes into trouble. So if we look at the GPU stream for this, what we see is that we have all of our Python, and then if we look at the GPU kernels, this is quite a sparse GPU stream. So there isn't really enough work in this model to fill the GPU, and so it's basically the Python executes or launches a kernel, the GPU immediately tears through it, and then it just waits. Sorry, is there a question? Oh. So these models are generally quite difficult to optimize, but I just want to zoom in on one example of where we can try to optimize them. We're not going to get much win, but it's still worth taking a look, which is that if we go to this.
Sorry, what GPU is this? Is
this is an A100. Yeah. I have managed to lose. Here we go. So here what we can see is a multiply followed by a sum. And if we go and we look at the source code, what we basically see is it's a times b dot sum dimension equals -1. Well, this sounds suspiciously like a matrix multiply, right? And this is a pattern that you'll see quite a lot in a lot of these ML models, right? You do a broadcast, and then you reduce down all of those dimensions, and that intermediate broadcasted tensor doesn't actually have to exist. Often there is a more efficient intermediate primitive. And so in this case, we can take a moment and actually do some micro-benchmarking to see what would this buy us if we, I'm going to skip some of the intermediate. I'll just briefly note the profiler can get you the shapes of your tensors out. And so the way that you would determine is this a good candidate for optimization is you would look at the shape and say, okay, if this is a big blocky operation, this is probably less likely, whereas if it's, although you can figure out the intermediate shapes to figure out if it's more memory intensive or compute intensive, and then use that to start your micro benchmarks and seed them. So I'm going to run these micro benchmarks in the background, and then we're just going to kind of look at the code that they're running. So there's three different ways that we can represent this x times y dot sum. So there's the way that it was originally written, and it's written this way because it's coming from a more general library that has to cover a broader set of shapes. You can write this as an Einstein summation, or you can just represent this as a vector matrix or vector product. And there's a utility in Torch to help you optimize this. It's basically a variant or a copy of the built-in time@utils timer, but it handles all of the Torch-specific things you have to worry about, like setting the number of threads and doing CUDA synchronization so that you are actually measuring the total time and not just the launch time. So if we run this, what we'll see, zoom in on it, is that our broadcast produce takes about 200 microseconds, and our INSUM and MATMOL are both a little bit faster because they're launching one kernel instead of two, because the time isn't in the kernel itself, it's in just the amount of time that it takes Python and PyTorch to launch the kernel. But there's another factor that you need to consider, which is we are not just going to be running this in forward. We are going to be running this in forward, and then those forward operations are going to put nodes in the autograd graph that are going to schedule future computations that will run in the backward pass. And the reason that I've put einsum in here is if we look at the backward, and I've done this with either A requires grad, B requires grad, or they both require grad, then what you can see is matmul is pretty much always extremely fast, right? Because we have efficient matmul implementations, it's one kernel matmul, you sort of get the best of all worlds. Whereas, in this case, the einsum is actually slower in forward backward, than the broadcast reduced, even though it was faster in the forward pass. And the reason is because it has to dispatch a more complicated autograd backward kernel. And that can actually eat up a lot of your time. So you need to make sure that you're taking this into account when you're doing your micro benchmarks. And I'm going to skip the actual splicing this into the code. I can make this available afterwards. But essentially what you see is you get a modest speed up from taking these two operations and folding them into one operation. Okay, all of this is this is optimizing the model as it's written, but you should also think about the actual model topology and hyperparameters as tuning knobs, because your goal is generally not to make this one thing run as fast as possible, unless you're, say, replicating a paper. Your goal is generally get the best performance. And so in this case, what we've seen is that we're overhead limited. So we can also just increase the size of the model, and that might let us train for less time. So if I just increase the number of hidden channels, then so the default configuration is 200. If I increase this to 600, it's a 3x increase, and then square the matmul, so it's 9 times more work. And what we can see is it's not really any slower to train, but what we'll see when we open up the trace is we still have basically the same Python dispatch, but when we look at the GPU stream, this is the, let me just make sure I am running. We now have, this is still not amazing, but we now have these, you'll see these, they often have kind of hard to interpret names, but things like Ampere SGEM or Cutlass kernel. These are the NVIDIA math libraries. So this is basically saying that we have produced a matrix multiply inside the linear layers that is big enough that it's now actually challenging, this is an A100, it's now actually challenging for the GPU to run on. There's now enough work that it can keep it satisfied for a while. And this means that in some of the regions, we can actually get a little bit ahead of the GPU and not be quite so overhead bound. Ampere and Onward also has a fairly nice feature called TF32 matrix multiplication, where basically it will do single precision matrix multiplies at a slightly lower internal precision in a 19-bit floating point representation in the silicon itself, and then give them back to you as 32-bit. So you lose a little bit of accuracy on the matrix multiply, but not as much, and importantly, not as much stability as going to a full half precision. And this is kind of easily exposed in the PyTorch API. There's just a knob where you just say allow TF32, and this just means all of the CUDA kernels will use TF32 under the hood. And then if we run this, it will, so I've increased the hidden dimension even further, but it's still going to run very quickly, and basically, again, I can increase it, but then the time comes back down because I use this lower precision. And if I look at the trace, what I'll see is basically just now these lower precision kernels running in the trace. Right, so you'll see a lot of, before we saw SGEM, so SGEM stands for single precision generalized matrix multiply. This is what you'll see if you're doing just straight FP32 matmuls. Now if we zoom in more, these Cutlass ones are basically PyTorch under the hood going and dispatching to the TF32. So that was kind of just a whirlwind tour of how to use the profiler itself. Before I switch gears and actually shine this flashlight on lit llama. Any questions? Okay. All right, so for lit llama, this is the library that we just released, and I'm just going to very quickly run through the training code. It uses Fabric, which we'll talk about. I've made some very modest changes to it just for the demonstration, adding things like profile. Key features of it. So first of all, it uses a strategy called FSDP. Essentially what FSDP does is it keeps a fraction of your model on each GPU, and then as you run the model, every GPU that doesn't have that particular set of weights gathers it from the one that does, and then when it's time to do backward, they scatter them back out. And this is implemented using Lightning Fabric. Otherwise, the training step is, as we'll mention, very generic. It looks like PyTorch, except instead of loss.backward, you have backward loss, etc. And then, of course, I've added the profile. So let's go ahead and run this. And what we'll see is, and this is running using the default configuration, which is 4 GPUs, and this is running on the 40 gigabyte A100s on this machine. And while this is running, I'm just going to skip ahead and go to one of the pre-baked traces, just because it can take a little bit of time to run. Use this one. Yeah. Okay. So if we look at this, what we see is, yeah, it's really unfortunate. This is such a low resolution. You have the forward pass, but then you have this very long backward pass. And if we look at where we're spending time actually in the kernels in the backward pass, we see these very, very long, right? Like these are, multi-second kernel stalls. And really no kernel that you're running here should take multiple seconds just to run one tiny part of the model. And if we zoom in under the hood, so one of the things that Profiler does is it captures the actual NVIDIA CUDA calls. What we see is there's a bunch of calls to CUDA free. And if we look at some of the other ones, like we have some of these resizes, we also see these enormous CUDA malloc calls. On the other hand, if we look at the compute stream, we see a slightly different story. So very little actual work matrix multiply. There's this region, which is nice and dense and looks fantastic in terms of a busy GPU. But then we have these very long all gather. So Nickel is the NVIDIA communication library. If GPUs are talking to each other, there's a good chance it's through Nickel. So if you see NCCL in a trace, it's GPUs talking to each other. And again, what we see are these enormously long communications between the GPUs. So what's going on here? So the first question is, do I just have bad interconnect? Often, like if you have bad interconnect, there's sort of nothing you can do. I'm just going to zoom out briefly. But NVIDIA SMI will just tell you. And if we look, right, NV12, these are basically peer-to-peer. So basically what NVIDIA SMI is telling us is, no, in fact, all of these GPUs have excellent interconnect to each other. They can absolutely satisfy this network traffic. Something else is going on. So the next thing, we have these huge CUDA mallocs and slews of CUDA frees. The next thing we should probably think about is this might be memory related. Now, recently, there was a tool introduced into PyTorch Profiler. Let me pull up the V2. Yeah. So you can tell PyTorch Profiler, record all of the memory allocations, but that's kind of too low level. I'm not interested in when was this exactly allocated and freed. I'm interested in the lifetimes of my tensors. And so you can have it emit this object, which is basically like, show me the life of the memory over the course of the run. And so if we run that, and it just emits as an HTML, we wind up with something that looks like this. So These are color-coded for the type of tensor, but this is not yet really hardened on FSDP, and FSDP is quite complicated, so it only kind of gets some of the types right. But in this case, it's telling us these are all parameters. So I have a block of about 6 gigabytes of parameters in my llama model. Anyone want to take a guess at what this larger static block of allocations is? No.
Gradients.
It's not gradients. That is a good guess. It is the optimizer state. We are training using AtomW. AtomW keeps two moving averages, an exponential and exponential square average. That means that for every element in your parameter, you have to keep two elements of optimizer state. And so that's why this is twice as big. If you were doing SGD with momentum, it would be the same size. If you were doing Atom with Amsgrad, it would be 3 times the size. And this is something that is very important when you're training these large parameter models, is that whatever you're going to pay in the parameters, you're going to pay several times that if you use one of these more complicated state-preserving optimizers. Now, if we zoom in here, we can see the forward pass. Forward pass is indicated by just this gradual increase in memory. Another thing to note that is specific to FSDP is we are creating and destroying things that it's calling parameters. This purple is parameters. This is the gather, right? So even though the logical parameters don't have to change, as far as the view of the GPU is concerned, it has to allocate a new tensor, put a parameter from a different rank in it, and then when it's done with that part of the forward pass, it can free it. So that's why we see this kind of spikiness around parameters that you wouldn't see with a simpler strategy like DDP. Now here is where we get to the gradients, right? And there are a couple ways we can tell they're the gradients. First one is as we get through the backward pass, right? So this decreasing sliver, right? These are our activations being freed as we go through the backward pass, and the autograd engine releases its references. But we're accumulating a gradient, and that gradient is the same size as the parameter that it is the gradient with respect to. So by the time we get to the end of the backward pass, we have accumulated, right? If this is x, we have already 3x from this. We've accumulated a 4th x here. And this puts us to about 27-ish gigabytes of total memory used on a 40 gigabyte card. But there's a lot of overhead. There's fragmentation. This is actually very close to kind of the limit of what we can get away with before the allocator has to start very aggressively reclaiming and doing things that it doesn't want to do to actually service all of the allocations. So there is a trick that you can do. If you think about the inherent data dependency of this operation, you don't need to wait until the very end of the backward pass in order to start applying your gradient updates and then freeing your gradients. It just happens to be the case that the API says first you call backward and then you call optimizer step. So if we take a little bit of an intermission, we can look at, I'm going to start by looking at a simple recipe that doesn't apply to distributed because the distributed one is somewhat more complicated. Essentially what we can do is we can say, I can have a hook that just applies the gradient to one tensor and then frees the gradient immediately. And then there's an API in the autograd engine where you can basically say, when you compute the gradient, please run this function. And one of the things that we have this function do is we have it free the gradient that it just applied after it uses it. And so if we go back to this plot, instead what would happen if we applied this method is that this gradient would be brought to this rank, use it, apply it, free it, and then we would not have this growth. So the version that works with FSDP is more complicated because FSDP already hooks into this mechanism. This is something that I've been in talks with the Torch distributed team, so it's going to make its way into a public API. But for the time being, you basically have to go in, grab some FSDP state, hook, basically chain your own callback on top of the FSDP callback, and then an important feature is that the FSDP, the way that it gets the gradients, it gathers them from all the ranks on its own stream. And so if you just naively applied the recipe that I just did, you'll actually get the wrong answer because the host will schedule all of the collection from all the different ranks. As far as the host is concerned, that's done. Now the GPU internally on its own stream is executing that work and scheduling it however it likes, And if you then schedule some more work on that stream, it will be ordered properly and it will be run after as it should be. But if you just fire it off on the default stream, as far as CUDA is concerned, it can order those however it likes, and it is free to actually apply your gradient update before you've brought your gradients from the other ranks. And so you won't converge, you'll get wrong answers. So initially what we do is we just force a CUDA synchronize. And this is not great. You don't really want to excessively CUDA synchronize, but what it buys us is it lets us ensure that all of this collection has happened, and therefore we can use the gradients immediately. And we'll do a little bit better at that in a little bit. So if we run this, I'm going to set the run going, and then we'll look at what the memory looks like. It is this one. Right, so this is a much nicer memory trace, right? We still have our 3x, parameter and optimizer state. There's no way of getting around that short of, say, offloading to the CPU, but that's the bandwidth over PCI really won't allow that. We still have our increase in the forward pass, but now, instead of this very large decrease in the backward pass, now we have a decrease in backward pass, as you sort of should, right? Because you're only operating on one parameter's worth of gradient at a time, but you are, in fact, freeing the activations as you go back. And so now, the slope for this is in the right direction. And if we go back to our terminal, what we can see is that our step time has gone from about 5 seconds, 5,000 milliseconds, down to about 850, 900 milliseconds, right? So just doing this, it's not even a particularly efficient way to do it. We got a 5x improvement. And where this 5x improvement came from is a combination of, one, if you are no longer near the ragged edge of being out of memory, the PyTorch allocator doesn't have to constantly try and free blocks and move things around and do all of this extra work, combined with the fact that as it's doing all of this extra work, it is constantly hitting the CUDA runtime allocator, which is itself beleaguered and has to do all of this shuffling. And this is how you get a 2-second CUDA malloc or CUDA free when it should take microseconds. So if we look at this profile, I have this running on every rank, so that's why there are so many traces. Question? Okay, so what we see are forward passes still very fast, right? Still lots of dense compute. In the backward pass, it's not actually terrible, right? There are these gaps, but you also have these large regions of very dense compute where the backward for a given layer is able to run largely unobstructed. And if we look at where these gaps are coming from, well, they're coming from CUDA device synchronized. Basically, so there's 32 layers on this model. And so on every block, we're forced to do a CUDA device synchronize, and we see a corresponding bubble as the GPU is basically forced to stop, synchronize the world. This is a very expensive operation in CUDA. And it doesn't let us schedule any computation ahead of time. Now, we're already peeking into the internals of FSDP, so let's peek a little bit further. We can look at the CUDA streams that it's using, and instead of doing a full device synchronization, I mentioned that it's fine if we do this before it's ready, as long as we tell CUDA that it has to be run after the thing that we expect to be ready. So if we look at a slightly better implementation of this, then what we can do is we can basically go into FSDP, look at the stream that it's using for these communications, and then just when we go and apply this optimizer, we just say put it on that stream, because then we know that it's run ahead of time. And now if we run this, there will be no synchronization. All of those gaps will go away. So let me actually go ahead and run this. This isn't really going to change the amount of memory we consume. All it's doing is it's letting us skip these host device syncs. So this should only take a moment to run. And while By the way, something that you'll notice, a couple things you'll notice looking at the individual step times. First, the first couple steps are always very slow. There's a bunch of lazy initialization that has to happen. Second, we've gone from 850 milliseconds down to 630 milliseconds. And again, this is just coming from the fact that those little gaps we've now taken out, and we will now, if we look at the GPU trace, we'll see fairly dense compute. And to sort of go further in this current 4 GPU configuration, what we would have to do is we would have to basically go in and look at the individual kernels and say, could we optimize these or could we make fusion? Basically, that's very heavy lifting. But one of the things that I kind of want to emphasize here is that even if we do all of that, maybe if we're very good, we could get a 2x improvement. Whereas we've gotten almost a 10x improvement just by taking away all of the ancillary things that are not the pure math and the pure attention, but that are standing in the way of the model kind of running free. So again, while this is running, the next kind of logical question to ask is, okay, all of this work has been to say, take a model that is kind of flirting with going out of memory and back it off enough that it has enough headroom that it can just run normally. So I can go to more GPUs. This machine has 8 GPUs. What happens if I do that? I think this has... I see that I'm kind of close to sort of over time, so I'm just going to describe what happens. If we go to more GPUs, we will get more memory, and then one of the things that we can start backing off is we can start backing off the way that we do activation checkpointing. So something I haven't talked about here, another technique, is you can recompute parts of the forward pass and the backward pass so you don't have to save that compute, and again, so you don't have to use the memory to save the compute in the backward pass. And this has to use activation checkpointing to run efficiently. Well, the more you spread out across GPUs, the more headroom you have, the less you have to recompute, and the more you can just hold on to from the forward pass. And again, as we go to more less greedy optimizers, so going from Atom to SGD with momentum and then going to SGD, we can go to a finer and finer grained checkpointing, where instead of checkpointing on an entire block, we can checkpoint on segments of a block. And then on the really compute-intensive parts, like the linear layers, maybe we don't even checkpoint those. And as our memory headroom goes down, and then we get back to it with less activation checkpointing, we get another about 50% off the step time. And that's how you shave an order of magnitude off the default settings of a LLM.